Think about the air inside the room you're sitting in right now. It looks completely empty, but at a microscopic level, it's absolute chaos. Billions of tiny, invisible gas molecules, like oxygen, nitrogen, and carbon dioxide, are constantly and violently ricocheting off each other, ekdam packed or fast-moving. Now, managing that chaos becomes a matter of life and death when we take that air underwater. Look at this vintage photo of an early scuba diver. She's relying on a specific mixture of compressed gases inside that heavy metal tank to survive. But there's a technical problem here. If you check the pressure gauge on that scuba tank, it gives you exactly one number, the total pressure. वो gauge आपको ये नहीं बताएगा कि सिर्फ oxygen का pressure कितना है या nitrogen का pressure कितना है. It only shows the final combined force. To figure out what's happening inside, we rely on a rule discovered by John Dalton. Dalton realized that as long as gases don't chemically react with each other, they completely ignore their neighbors. एक gas दूसरी gas को पूरी तरह ignore करती है. Dalton's law proves that the total pressure of a gas mixture is the sum of its independent parts. This allows us to calculate the influence of a single gas by looking at it as an isolated contributor to the whole. Let's look at how this additive rule works. If we take two isolated gases, gas A in red and gas B in blue, each exerting its own pressure, and we force them into the exact same container, their combined pressure is the exact sum of the original two. This brings us to a term called partial pressure. In a gas mixture, partial pressure is the pressure a specific gas would exert if it were entirely alone in that container, with all the other gases removed. We can see the official mathematical breakdown in these handwritten notes. The formula right at the top lays it out. Total pressure, or P total, equals P1 plus P2 plus P3, and so on. To calculate this, we use a variable called the mole fraction, written as chi-A. Think of this as the percentage of the crowd. If 60% of the individual molecules inside a tank belong to gas A, then gas A holds a 60% mole fraction. It owns 60% of the pressure. Looking slightly further down the page, we find the calculation. The partial pressure of any single component, like gas A, is its mole fraction multiplied by the total pressure. What this tells us is that a gas's individual strength in a mixture is not determined by its chemical type. Its influence is strictly dictated by its numerical share of the total molecules. But what happens if we take two different gases that start at different volumes and pressures and combine them into a single, newly sized space? Before we do the math, we have to lock in one condition. For any of this to work, the temperature of the system must remain constant. Agar temperature change hua, till pressure calculation asar detayaga. Provided the temperature stays stable, this middle section of the notes shows the solution. The new total pressure P is calculated by adding the product of each gas's initial pressure and volume, then dividing by the combined total volume. Even when you manipulate both the volume and the pressure across multiple different gases at once, the resulting total pressure remains entirely predictable as long as the thermal energy doesn't interfere. Dalton's law provides three physical rules of thumb regarding mass, volume, and moles that show how these mixtures behave in practice. Rule number 1 involves equal masses. If you have two different gases sitting on a scale and their masses are equal, the gas that is chemically lighter will exert a higher partial pressure. This happens because of the particle count. A lighter gas requires significantly more individual particles, more moles, to reach the same weight as a heavy gas. Since pressure is driven by particle collisions, more particles mean more pressure. Rule number 2 focuses on equal volumes. As highlighted in the conclusions, mixing equal volumes of different gases means partial pressures are nearly identical. And Rule 3 is the final takeaway. With the exact same number of moles, partial pressures are identical, regardless of mass. In a closed system of non-reacting gases, pressure operates as a strict democracy. A gas's pressure doesn't depend on its weight or chemical identity, but purely on how many molecules it contributes to the space. One molecule equals one unit of influence.